Hi guys, good afternoon. Yes, so as observed, I intended to um, do a recording so it can facilitate or aid in your assessment. So I'm going to look at PET sample test today. Then I will also look at correlation and regression analysis if time permits. So why we have to consider PET sample tests as a data analytics tool for research work is simply when we are looking at a study that we want to look at possibly analyzing a pre and post event to test an hypothesis to whether there is significant change in the existence of a presence of before and after, then we can use the PET sample test. One key example we can look at is the whole COVID vaccination as maybe for some clinical tests. So we could look at individuals who have contracted the COVID, and the doctors may say before the vaccination, they want to look at their condition in terms of looking at their temperature. So data will be collected on their temperature before each patient again will be given the vaccination. So we want to look whether or not, find out from our test whether or not the vaccination is effective. And one way in doing that is to look at their temperature before vaccination and temperature after the vaccination. Then we can test for that hypothesis. But we can assume that the vaccination will improve their medical condition in terms of the temperature. So that would be possibly the hypothesis to say that, of course, we want to expect a significant difference when in the use of vaccination on these patients with the peculiar issues with COVID. So PET sample comes in here. We are looking at the differences between the population means. So we are looking at means difference when we are looking at before and after or PET sample, as I said. So the focus is to know the population difference, where mu D is what the difference between the population, so that we can always assume that we are mu differences between the pairs of values. And for that matter, the data we have should be normally distributed. If this is achieved, the focus is to develop an hypothesis. Whether a one-tail or two-tail test, we should be able to check that. So for PET sample, if we want to test for the hypothesis, our focus is to look out for using the difference as in the D bar, as we've observed using the, again, when we're looking at the single sample or two sample, our focus was to look at the sample mean, which we define as the X bar. So for mean difference, we are also defining our X bar here as the D bar. And D bar would therefore, we are looking at the summation DI divided by the sample size, where DI is looking at the difference between, for each ith observation, we are looking at the difference between the before sample minus the after sample for each ith observation. So when we are able to find the differences, the summation of these differences will what will result in our DI, which can help us compute D bar. So, for instance, if we have Ufi here, Aba, and Ajwa as temperature, as I said on the COVID issue, Then maybe if this is, we can say 90 degrees before the vaccination was given. After the vaccination, maybe we are looking at 75 degrees in terms of temperature, 120, and we are having 90 here. Then we have 80, but we are having 120. So if these are the observations we have, so DI, we need to find the difference between Kofi's temperature before and after. So DI for Kofi, so DK more or less DA and DAD. This is going to be 15. Then we're going to have 30. And we're going to have here minus what? 40. So when we say summation DI, then we are summing 15 plus 30 plus minus 40 to give us the numerator more or less here. So this is going to be 45 minus this is 5. So my DI is 5. So when I come here, D bar is going to be 5 divided by the sample size 1, 2, 3, 3 observation, which is going to be 3. And that will give me my D bar respectively. So at all time, it is the ith observation that we have for each respondent. In that matter, for research work, each respondent will give us a TI. When we are able to observe this, then we can also go and find the standard deviation, which is also defined as this guy here. So in terms of this, again, we are repeating summation DI, D bar, all of them 9 minus 9, n minus 1 square root will give us the standard deviation. So this will be the standard error of the D bar. That's the mean difference. So standard error, the whole of the denominator here is the standard error. By way of computing the numerator in the t-test, we assume that the population mean difference is equal to 0. So in effect, T will be equal to D bar divided by the standard error of the mean, which is the standard deviation divided by the square root. Okay, then we should know, usually a lot of the time when we are looking at paired sample, we are dealing with 2-tail test. So the alpha is also divided by 2. But this is the same population. So it's not N1 plus N2 minus 2. No. We are only looking at N1 minus 1 to find the degrees of freedom. Once we have these observations properly represented, these text parameters, then we can go on to test for the hypothesis respectively. And again, as we've been observing, we have data available. We are going to use SPSS to run the entire analysis. So the categorization of the data we have is very important. We've gone through this through the entire semester. So this is just a summary analysis for you to also, as you do your revision, this can help for that respectively. Okay, so let's go through one after the other. So let me close this. Yes, and come back here, undo. Sorry. So, yes. So this is the hypothesis. Let me clear this side. Okay. After this video, if you watch it on YouTube and you still have questions, do reach me through my email as indicated in the course outline for more clarity, if that is okay for you guys. All right. So let's make progress. So this is a research work that we did, which I still think is relevant to our conversation. We want to look at the whole buzz about fintech and how Gen Zs are whether getting here ready to use it or not. The study was far back as 4 years ago. So we are looking at their perception before and after. Okay, so what is their perspective? before maybe a trial to use the system, and after using the system, would they be willing to use this? So we assume that the research objective is going to look out to explore dominant fintech applications in Ghana, then to investigate the adoption and usage of fintech applications in Ghana. We hypothesize to say that in terms of perception, that will show there is no readiness. The MUN-D says that there is no significant readiness in the adoption. MUN-D, that's the HO. Then HA indicates readiness in the perception to adopt and use fintech application. We use the mixed method approach, and the sample size significantly is 21. So this qualifies for a t-test. We use a convenience sampling technique. This is the data that we have. We've discussed this data already, and we looked at how to code them respectively. So let's quickly go to SPSS. Let me share my screen. Okay, so this is what we have here. So quickly, we have gender as a category, and we know gender is a categorical data, which is nominal. So gender again, just to, and in terms of the responses, we have female. Let's use female for 1, and let's use 2 or 0 or as male, and also indicate here, ensure the measure is nominal. Then we have fintech type to also understand that fintech type. Yes, coming. Who is there? Please, who is there? Hello? But I'm asking who is there, you're not minding me. Who is that student? Who? I'm asking who is there. You are not talking. How would I know it's a student? Student who? I mean, that's what I'm asking. Student who? Please, what's the issue? You're a research student. You're a research student. Were you coming to class? I never see you in class. No, I didn't register. I registered late. But you were not coming to class. No. How do you pass the exams if you are not coming to class, madam? How do you pass an exam you want to write, and yet you never showed up in class? So all the instructions have been given in class. You are not part. How do you intend to part? Explain that to me so that you are in level 400. But you never come to my class. That's the strength. Even when you're in 300, I never see your face in class. Yes. So, and you didn't pass the exams, and you are repeating the same thing. So how are you going to pass it? Did you go to marry? Do you work? A nursing mother. But that is the more reason why you are supposed to contact the lecturer from day 1. But you've been there few weeks to exams. You are now showing up, slide first, you are now showing up for. But you know that you are going to write the exams. Or you didn't know that you write exams. When I paid for the visit, it wasn't showing. You're not getting, I said, you know you are going to write for exams. Didn't you know? So if you know you are going to write for exams and you sat down, waited, exams time is getting close. Whatever was given, direction given to student, it didn't show up. And suddenly you are in my office to say that you're a recent student. What exactly do you want me like to do? From the beginning of the semester, you've been coming here. So, yeah, but you can't also just jump into my office in the name of what? Coming to look for me. But you can't just come to my office that you are looking for me when I don't even know who is coming to look for me. I don't understand you people, but whatever you people plan, that's, for me, I don't have a problem with that. But the university has a structure, and everybody who intend to be in the university must work with the structure. So what exactly do you want me to do? What? Now, what exactly do you want me to do at this stage? I should help you out. And what about those who have been coming to class? That between the two of you, who should be helped? I'm in a class, actually. So I'm doing a recording for my student. I've muted the class. Hi guys, sorry for the interruption. So our data, I've entered the data just as we've been doing in class. So everything is set for the analysis to be conducted. If you can see my screen, let me share my screen again. I hope you can see the screen. So as observed, we can look at the data entries depending on what we want to look out for. But I'm going to focus on the pre and post event analysis, given that this is what we want to observe. So simply, you go to analyze again and go to compare means. We'll see PET sample t-test. Then we select the variable as defined for pre and variable as defined for post. Then that's all we can do. we are looking at 95% confidence interval. So we testing hypothesis at 5% significance level. So continuing here. Then we click OK. Let me share my screen, and I hope you can see that that's for the output. Okay, so mainly we are looking, I'm going to just focus on the paired sample t-test, but we can say for the individual observation for pre and post, these are their respective sample statistics in terms of the mean for pre-rating and mean for pro-rating. The sample size here is 21, then the standard deviation. Then we have the paired sample correlation. We can, this is just part of the data. So you see the correlation showing negative. It's even low, 1.146. That's almost 15% correlation with the data. But our focus is on the paired sample test statistics. So if you can observe carefully, we were able to compute, let me indicate, we were computing D bar, we computed the standard deviation. So therefore, if we are looking at the test statistics, we are saying it's going to be D bar divided by the standard error of the mean, which is standard deviation over this. Each of these parameters are shown here. This is our D bar. So D bar is here from the data. This is the standard deviation. The standard error of the mean here is the standard deviation divided by n. Then we have our t-test, which is giving us this guy here. Degrees of freedom, as I said, is n minus 1. So you don't come and sum these two to make it 42. No, that's not your n. Your n is still 21 minus 1, which is 20. Then this is the p-value for the text statistics that we have here. Of course, for assessment purpose, as we observed, we can say that to develop the hypothesis, then we are looking at HO as we've done, mu D is equal to 0. We say that there is no significance readiness for adoption. Then HA mu D is not equal to 0. This shows that significance readiness for. And given the p-value, which is the focus, we are looking at when our p-value is less than 0.05, in this case divided by 2. So any p-value we have from that's the probability for the test statistics. If it is less than 0.025, then we will reject the null hypothesis to indicate there is significance readiness based on the perception from Gen Zs. If p-value is greater than 0.05, 0.025, then we fail to reject the null hypothesis. In that case, the HO stand, which says that there is no significance. So in our results here, what we can say is that the p-value of 0.186 is greater than 0.025. So we fail to reject HO. And I remember in class, I've told you because our assessment is going to be on Sakai, you don't have to type all this. So in this case, I expect that you type fail to reject, or fail. That will be your answer. If it is reject HO, you only type reject nicely in the space provided. What you'll be doing is to look out for how do we compute D bar from this given table? How do we compute the standard deviation, the standard error, the T, and so A, B, C, D, E are most important. We could decide that some of the figures here will be hidden, especially the t value here could be hidden, or the standard error will be hidden, or the mean will be hidden. I mean, whichever one. So that you should know that if standard error here is a standard deviation divided by n, and this is hidden, you should be able to compute the standard error, because this is your n as the sample size given the standard deviation. We are looking at 2.548 divided by the square root of 21. That will give you C. So in effect, you should know, if given this formula even as your T, then we know that to find the standard error, which is what I'm trying to find here, standard error is going to be SC will be equal to D bar times T. And at the same time, if we are to find D bar will be equal to standard error. Sorry, this is divided by T, not times T. Then the D bar here will be equal to T times the standard error. So you should find a way to substitute this to compute that. And if we are to find degrees of freedom, we know again that is E is equal to N minus 1, which can help solve this. So any of this could be removed, or 2 or 3 will be removed, and you'll be asked to compute that respectively. Then you should be able to indicate again whether, based on the p-value of the test statistics, we should reject the null, or we fail to reject the null in given the scenario or given the test that we need to perform. Yeah, so that should be for paired sample test for your assessment. So kindly remember these guys in terms of the data. Or you could also be given, again, the data in its raw state, and I could still ask you to compute the D bar. The D bar here, given the data input. Standard deviation could be there. The rest, don't worry about the upper and the lower limit degrees of freedom that as in the confidence interval yet. Significantly, we are looking at these guys for this. All right. So this is for paired sample test. You can look for the multiple regression as, let me share my slide again. Okay, so this one, good. ANOVA, we've discussed it. I've given you instructions on how to use ANOVA again with SPSS. I've given you all the output. So we can discuss correlation and regression. Importantly, for the groups that I missed, this also is supposed to support your learning, so that if you have any challenge, kindly get in touch. So correlation, why regression? We'll discuss this extensively. And again, as I observed in class, it is important that before we even go on to develop a model and do the estimated regression equation and begin to do that, the assumptions under regression must be fully met based on the data that we have. So we have to check for linearity. We have to check for normality, heteroscedasticity, autocorrelation, heterogeneity, and multi-collinearity. We explained this extensively, and remember indicating that we could look at clearly these assumptions, and based on the data, we can test them respectively. So I observed, especially for linearity, how we can test linearity if we are looking at the dependence between X and Y, where we always observe that linearity assumption is to evaluate or observe that Y behavior is extensively influenced by X for a simple linear regression. We can check linearity assumption or test this assumption by using, we can look at using the scatter plot. Okay, we can use scatter plot to check. So when we plot, we should be able to see some form of linearity here, so that if you draw the line of best fit, we know specifically. And this could be positively linear, or we can also have negative linear, depend on what the data is exhibiting. We don't want to see any form of curved linear relationship, which defeat the purpose of checking for linearity. So either scatter plot, or better still, we can also look at the correlation coefficient, okay, between X and Y to check the strength of linear relationship or strength of association between Y and X. Then we can also look for normality and homoscedasticity. Our focus here is to look out for homoscedasticity. We want to ensure that the variation between the dependent and independent variables are constant. So constant variance. That means that we don't have a problem with heterogeneity. So here for homoscedasticity, we can use the variance to check for that. Okay, then for normality also, which is also a key assumption, we can use the histogram to plot for and check for whether the data we have is normally distributed. Okay, or we can even use the normal probability plot to check for normality. Then we are talking about autocorrelation. We don't want to see any problem with autocorrelation. So there should be no autocorrelation in the data, especially for the errors of the independent variable, the variation for them. We can look at the data point to check that. How do we check for autocorrelation? We can use the Debye-Watson test to check for autocorrelation. And by threshold, we expect between 0 to 4. If the Debye-Watson value is between, let's say, 1 to 4 or 0 to 4, then we can estimate that there is no issue with autocorrelation, especially when we look at the independent variable, the data point, or we are looking at the errors are independent. You pick for data point for each of the variables that you have, and we should expect that. So we can use Debye-Watson to test for that. Then lastly, we can look out for checking for multicollinearity. We are looking at the independence of the independent variable. So when we pick pairs of independent variable, we want to test the strength of association. So we can use the correlation coefficient. So when you go through the correlation matrix table, we need to check the correlation coefficient between two independent variables at a time. The reason is that if there is a high level of association, which means that we are dealing with singularity, which is a big issue as far as the independence of the independent variables are concerned. Two independent variables behaving or having high level of correlation simply indicate that they are behaving or their strength in the model is the same. So one must be taken out, or if it means that both needs to be removed, then it has to be removed from the model and we rerun again. So mainly we'll come here to say that we should use the correlation coefficient to check for the strength of association. That's the first test. The second test is to use the variance inflation factor, okay, or we say the VIF. This is a threshold that we can consider. And for VIF factor, so that if I pick the pairs of independent variable and we are checking for VIF, we are also looking at a threshold between, if it is between 1 to 5, there is the level of singularity is low. But from 5 or to 10 or above 10 is giving us a problem that we need to check. So between those two pairs of independent variable, if we check their correlation coefficient, let's say it's above 80%, which is a key issue, then we can use the VIF further to check which of these variables needs to exit from the model respectively. So ladies and gentlemen, the assumptions are critical at all time when we want to run correlation and regression analysis. Linearity, normality, normal stochasticity, autocorrelation, and multi-collinearity. So let's observe this. Perhaps in the exams, you should be able to, for each of the assumptions, what to be the possible test that we can use to observe these assumptions one after the other. So kindly note that, and we can make progress from here. So again, we want to use SPSS to run the entire analysis. So the analysis must show the correlation matrix, that is for us to know, number one, the relationship between the dependent variable and the independent variables. And my example, we are going to look at, as we said earlier, we are looking at a cross-sectional data and not a panel regression analysis. Today is just a cross-sectional analysis throughout the conversation. So let's observe this quickly. Okay, so let's see. We explain what we mean by regression model and estimated regression equation. At the stage of developing or differentiating between dependent and independent variables, we should be able to develop a regression model. So wage, given that the indexing of I goes to the observation, is my dependent variable. Then the beta naught is more or less the constant, which in the model explains that in the event that the changes in the independent variables remain 0, okay, the total wage bill will be explained. The total value of the wage will be equal to the beta naught. So beta naught is just explaining the total value of the dependent variable as a result of a 0 unit change in the independent variables. So education, experience, position, and ability are all independent variables in the model. And this type of representation means that each variable is represented or is numeric. We are dealing with numerical data throughout. I also explain if there are categorical independent variable that needs to be transformed to dummy variables. That has been explained. The U here is the error term, which significantly indicates that beyond the variables that have been considered in this model, those that have not been considered, more or less the error is being controlled or mitigated by the mean here, or the error term shown here. So BP is also a regression model. QD prediction is also a regression model. Then the last one is what we call the estimated regression equation. This is when we have been satisfied with the data, we've checked for all that, then we can run or perform the analysis. We should go back and check the coefficient table to develop the estimated regression. In fact, this will be our predictive model. so that where a person's education level changes by a certain value, experience changes. So HR may decide that for every time you improve or you go to school, from undergrad to master's, there's a score given, experience score given. When we put all these changes in the score, we can be able to predict wage in the future. So in the HR budget, they can look at this as a predictive model to improve upon the wage bill every year. Otherwise, if there are more variables, that can also be considered. So ladies and gentlemen, we should be able to explain in our methodology, especially the model. When you write the regression or you are indicating that your analysis is going to be you're going to use regression, then we expect why regression, why the tool is necessary. Then you identify the dependent, independent variables for a multiple regression to estimate or develop the regression model and explain them one by one. Beta 1, beta 2, beta 3 more or less are the coefficient of the independent variable. And this is a multiple regression model. Okay, so let's quickly go to the data. So we've observed all the others. So this is the data I want us to look at. And we are looking at house prices in Boston. So that given the data, the last one highlighted here, median value of owner-occupied homes given in thousands of dollars. That is given as my dependent variables. All the others are the independent variable. Among them, we have a dummy variable called Charles, which says that we're looking at Charles River dummy variable. So if a house is closer to a river or Charles River, then we can say that we'll give that house 1 if the track is bounded by a river, otherwise 0. So as we observe, this has only 2 levels. So we need 1 representation in our model. So given this explanation, we should be able to develop our regression model in this way. So this is my regression model given here. Okay, and this example, I use Excel and Python, but in class, we all decided to use SPSS. So I'm going to take you back to my SPSS. We copy the data. Data is already in Sakai. So you can go to Sakai and copy the data and just put everything in SPSS, then we are good to go. So let me show you my Excel sheet. This is the Excel sheet giving our data here. So again, this will be a dependent variable and all the independent variables are captured here. We can go and copy this into SPSS quickly. Let me copy this, paste it here in a transpose form. This is what I need. We can copy this. So let's go back to SPSS. Okay. We can use the same. Let's just stick here. We don't have to create a new one here. So I come here, just paste all of them here. So this is what we have. All are this quantitative data. So we change the unknown to scale, one after the other. All right. So that's what we have. Like I said, this is a ratio data. So you don't need to come back here in terms of the value and come and define 1, 2. We can just upload the data straight into SPSS. Charts is not with decimal. Tax is also not with decimal. RAD not with decimal. The rest are all with decimal. So we go back to Excel. As observed, we can select from row 2 for all of them. But again, I've told you we can work smart. Just copy, select this and copy here. go back to SPSS. Then we go to our data view and paste it there. Okay, we don't need this. Can clear this ones. Oh, my bad. I come here. So let me go back here and just focus. Let's focus on this data. Okay, Control C, back to SPSS. Then Control V. Yes, so our data is ready here. So we can quickly go through the analysis. So if you can see clearly, again, let me try and see if I'm sharing right. Okay. So we go to analyze again and just go to linear regression and look for linear regression. In this window, the linear regression window, everything is defined. So this is our dependent variable. So we click and check into the dependent variable. These are independent variables. Also check it there. We can look at statistics. So by default, we need to check the model fitness and the estimate as well. So let's pick the descriptive statistics. We can also check for collinearity diagnostics and covariance matrix. Then we check for Devin-Watson for autocorrelation. We can go and check that. Go to plots. We can check histogram, normal probability. Then again, we can look at the prediction and the dependent variable. Then we click OK to continue. We don't have, again, 5%. I explained this stepwise, the backwards to the class already, where stepwise we look at only including variables, that's the independent variables that are significant. So those that are not significant will not even be included in the model estimation. Then backwards will include all of them together. Then we'll further look out for those that are only significant and including the estimated model. Okay, but today we just use we won't select any estimation method. From here, we can only click OK and run our analysis. So let me show you my output. Good. So this is the output. We have our correlation matrix table, descriptive statistics, correlation matrix. So because we didn't select any estimated method as I indicated, all variables have been entered. And this is our model summary, which is a table very useful for our analysis, same to ANOVA. And we can look at our correlation coefficient table. You can also see the variance inflation factor, where we have to check for multicollinearity and which variable must exit, and the significance of the correlation. This is the collinearity diagnostics. The charts also here can give us whether we are dealing with normal distributed data. It's also showing here. That's the histogram. Then we are checking for the issue with homogeneity, homoscedasticity. So we are looking at the constant variance also as well. So what we are doing today, again, is to focus on key aspects and of the output and how you're supposed to analyze it. Typically for your research work in the long essay, you have to report mainly on the table, okay? And each one must be given proper explanation as to what they mean. So we start with the correlation matrix, okay? Then one, we need to check for the level of association and the significance. So in the first section, you see, and again, we discussed the Pearson product moment correlation as the key tool to check for the strength of association. So you can see in the first the second column here, you have the MEDV, which is our dependent variable. All variables and compared to themselves perfectly correlated. So that's 100%. So that's what you see diagonally 1 throughout. The strength is 100%. Then we should be able to check the strength of association between the dependent variables and all the dependent variable and all the independent variables. So respectively, MEDV and CRIM, that's almost 39. Yeah, that's 39%. So that's 39% strength of association. Then again, MEDV and ZN is 36% correlation. So these are the correlation coefficients. MEDV and INDAS is 48% negatively correlated. Then MEDV to and CHARS, that's 19, also positively correlated. NOx is this. What I'm doing is just to indicate the strength of association. By this, we should be able to tell the independent variable that is strongly correlated to the dependent variable and the one that is also least correlated to or with the dependent variable. So by doing that, LSTAT is strongly correlated and CHARS is the least correlated independent variable with the dependent variable. So we can indicate them one after the other. So pairs. So we can say between between L strongly correlated LSTAT and MEDV. Okay, the association is what? 74%. That's the strength of association. And again, as we said, it's a negative relationship. Then the least correlated is going to be between CHARS and MEDV, which is what? 18% strength of association. Okay. Then we've discussed that we need to ensure that we don't have issue with multi-collinearity as a key issue. This time around, we are checking pairs of independent variables. So I should be able to pick CRIM and ZN or INDAS and CRIM and estimate or indicate the association. So I have to comb through now because we want to avoid multicollinearity. Which pairs are giving us high strength of association? So that between CRIM and ZN, this is 20%, 41%, 6%, 42%, 22%. So we don't have a problem with multicollinear between CRIM and all of them. So that's what you do. You pick ZN and do the same. INDAS, do the same. I could see here, you see there's a 91% and 91%. So we can trace that this is tax and this is RAD, or this is RAD and this is tax. So between RAD and tax, the strength of association is 91%, which gives us reason that these two, there's issue with singularity. Okay, high multicollinear between these two. And therefore, one of them, both of them, they are performing the same thing in the model. So both of them must exit or one must exit. But first, we have to go and check the variance inflation factor values for each one of these independent variables. And as we said, the threshold, we are looking at 10 and above, or we can say 5 to 10. If anything, means that there is, by theory or by literature, there is an issue. So we go and check the table that is going to give us the variance inflation factor to test for these two and eliminate one of them respectively. At this section, we are only going to identify which of the independent variable will possibly have to exit so we can rerun the model again. So we go to the coefficient, table, this one. Then we can see our VI, variance inflation factor here. Our focus is on tax and RAD, which we have them here. So you could see that RAD is 7.45 and tax is 9. So between these two, the possible one to consider first to exit from the model will be what? Tax. So tax VIF factor is greater than that of what? RAD. If we run the model again and RAD is behaving or relationship with other independent variables is also high, then that calls for also considering RAD to be out of the model. So systematically, this is how we can check for multicollinearity. First of all, check the relationship in the correlation matrix table. Then after that is carefully observed, we can go further to discuss which one must exit from the table. So significantly, the correlation matrix table helps us to understand or give an indication of the possible strength of association. And as we said about the linearity, we must also show that indeed the dependent variable, which is MEDV, behavior is influenced by either one or more of these variables that we have considered. All right. From here, I'll go straight to the model summary table. Where is this? So yes, this one. The model summary table will also help us to understand, one, whether or not the combination of the independent variable we have strongly affects the dependent variable. Then we can look at the testing for autocorrelation using the Durbin-Watson test. So the first thing we look at is to go and look for the R-square value. And this is also called the coefficient of determination. Why do we need the R-square? Since we have indicated that these predictors, these 12 independent variables, have some impact on the dependent variable, we want to know by how much variation they affect the dependent variable. So given R-square of 73%, we are indicating that 73% variation or changes in the dependent variable, which is MEDV, is explained by these 12 variables that we have indicated, or these 12 predictors. So that the remaining 27 can also be predicted by other factors, which are being mitigated by the mu or the error term. So at all time, we are saying that 73% changes in the house prices in Boston is as a result of these 12 guys, which are influencing MEDV in the model that we have. And that is why we need a R-square value. So a high R-square value also shows that there is high variability. The variability for the dependent variable are due to these predictors, which is very good here. The adjusted R, why do we need it? In case we decide that we want to improve or increase these predictors, we want to add more predictors to the model, then possibly we may be having the adjusted R-square can help us understand that per the adventure that we are introducing more variable, those values there will be also predicted by the R-square, the adjusted R-square in the model that we have, respectively. The square root of the R square is what will give us the R, which is the multiple R. Then we have the Dublin-Watson test here. And as we said, because we need to check for autocorrelation, the Dublin-Watson test comes in to help us understand whether the issue with autocorrelation is dealt with or otherwise. And again, per the threshold, if the Dublin-Watson value is within or between 0 to 4, it means that we do not really have problem with autocorrelation from the data that we have. So given this Dublin-Watson value, then we can argue that we do not have a challenge or problem with autocorrelation in the model or the data that we have, respectively. Okay, so that is also the key importance of having the model summary in our regression model. Then we have the ANOVA table. Why do we need an ANOVA table? Because we've indicated that when we put these 12 predictors together, 73% of the time they are influencing the dependent variable. We need to know its or their significance jointly. So we can look at the joint significance using the P value from the ANOVA table, so that we look at the P value here. If we have this P value, which is also less than 0.05, then we can say that all the predictors put together or jointly, so they are jointly significant in the model that we have here when we put all of them together. Better still, from the ANOVA table, R square here can be computed given the ANOVA table. So we can say R square will be equal to SSR divided by SST, where the R here is the regression, which is this one. Okay, this and this. So if we pick this and divide it by that, it should still give us the R square. So if I should add this value here, hide it, and ask you to compute the R square, then you should focus on using SSR divided by SST. Okay. The degrees of freedom between, remember the number of predictors. Then for this one too, we can compute the N minus K minus 1. K is the number of independent variable sample size. And we know how F computed is also derived from our previous section. But the focus here is to use the test for joint significance with the model, so that as far as practicable, if your p-value of the F test statistic is less than 0.05, then we'll conclude that the predictors put together here, their impact on the dependent variable are significant, jointly significant, respectively. So kindly note that. Right. The last table I'll discuss is the coefficient table. Okay, and why do we also need a coefficient table? As I said, we can use the coefficient table to develop the estimated regression equation here. We can use that one because for now in the model, as we observed, we are only saying that MEDV is equal to beta naught plus beta 1 cream plus beta 2 all the way to beta 12 to LSTAT. Now we know the beta values, which is given in the coefficient table. So you can see this is a constant. So this is my beta naught. This guy here is my beta naught. This is my beta 1, beta 2, beta 3, beta 4, beta 5, and all that. So that when you are asked to develop the estimated regression equation, or you know that the constant beta naught is here, Then this cream, beta 1 times the cream, beta 2 here times it. So we can use this one to now predict. So when we look at the predictive model for house prices in future, we have to depend on the beta values here and multiply them with their respective independent variable. Then we can have the standard error given, then the t-test. Beyond the estimation, we've already observed that the predictors jointly are significant. Now we can use the coefficient table here to test for individual significance. Because it's not enough to say they are jointly significant, but how do we check for individual? If you pick each variable, what is their impact specifically? And that is why we also need a t-test here and the significance level. Any variable, especially from the side here, if we say that a variable in the model is significant, means that the p-value of the test statistics is less than 0.05. So you can identify the number of variables, that's the independent variable, that are individually significant in the model, and those that are not significant. Not significant, not significant. All the rest are what? So almost 10 independent variables are significant, 2 are insignificant in the model. Okay, so that's what we can also look out for. These are the VIFs as we have observed. We've explained these VIFs already. So mainly we can look at this, but it's also suffice to say that our T computed here, okay, this guy is giving us my T will be equals to the coefficient given I divided by beta I, will help us to compute the T test statistics here. So that if I pick cream, this is my coefficient, and this is my standard error. Okay, so sorry, this will be standard error given I. Let me rewrite this again. So my minutes. Let me just write it here. So we are saying that our T, this guy here, is equal to the beta value. Okay, so I'll say BI, which is the coefficient, divided by the standard error I, given I goes to the respective value for the independent variable. So here means that cream, the value here for here, this is minus 1.121 divided by 0.033 is giving us the minus 3.63678. Let me just take these guys down. Just hope this is clear to everyone. So again, we are still looking at here. So T is equal to the coefficient of the beta. That's why I said, let's just say this. So beta I divided by standard error means that we can also decide to compute just the standard error, the coefficient. So the standard error of the values here will also be equal to coefficient of that's the beta I divided by T, or coefficient here will be equals to T times the standard error. So ladies and gentlemen, again, you will be given some opportunities in the assessment. Maybe we can hide this guy here. and asks you to compute this. Let me take these guys off. Let me just come back here. So here. So if this is giving us A, this is also hidden, is giving us B. This guy here is giving us C. This guy here is giving us D. Our friend here is giving us D. And this is giving us E. You should be able to compute the missing values. Should you be given them in the table? So you can use these guys to compute that. Again, change of subject from the explanation. So one by one, you may see significantly for assessment purposes. I may showcase the coefficient table, the ANOVA table, the model summary table. Then I can also include the drawings. I can also include the correlation coefficient table, depending on what. Again, you could be asked to use the coefficient table, this guy here, to maybe predict the value of the dependent variable. Given the changes in any of this, we know you should just have to multiply. If this is 2, Knox has changed to 2, so 2 times minus 18.76 times 2, you put a value. So when we add all of them together, it should give us the total value for the dependent variable respectively. Okay, so this is what I wanted to share with the group. I'm uploading this. So go to YouTube and watch the video for your assessment. So thank you very much. Though I would say for joining. Thank you very much and have a blessed weekend, and at the same time, all the best in the exams. Bye-bye for now.